Ladies and gentlemen, our morning keynote concerns big data. Now, the first documented instance of processing big data and getting something out of it was published way back in 1662. In the 1550s, the city of London suffered from recurring epidemics of plague, bubonic plague. And they then started publishing on a weekly basis so-called bills of mortality, which shows you so many guys have died, and these are the causes. And these were widely distributed, they cost a penny each, and there were some very interesting causes of death. One of them was horseshoe head. Another one was eaten by lice, and teeth, and purple, and there was the rising of the lights. And the one, my favorite, is overjoy. I wouldn't mind if that's my cause of death. Anyway, a guy called John Graunt then took all of that raw data, which just raw data, he added information from parishes around London, additional information, collated all of that, and he then published a book, which he called, let's see if we've got it, Natural and Political Observations in 1662. What he basically did, he processed the raw data and got information out of it. Trends, differences in geography, root causes, and so on. Now, we are living currently in an era of big data, overwhelmingly big data. For instance, the SKA, once operational, is claimed to generate about 50 gigabytes per second. And it's not an optical telescope, it works 24 hours a day. What on earth is anybody going to do with that data tsunami? Problem. The Large Hadron Collider generates something like 25,000 gigabytes per day. In fact, the Large Hadron Collider generates 600 million particle collisions every second. And they filter and remove about, I think it's about 5 in a million that are actually accepted. They still get 25,000 gigabytes per day. Other people estimated that in 2020, 2012, 5 years ago, about 10 petabytes per second were generated every second, and that was long before the Internet of Things. What do we mean with big data? It's a big data set so large that traditional methods of processing it doesn't work. People talk about the 3V model. Big data means high volume. We spoke about that. High velocity, real time. High variability, text, image, audio, video, whatever. And then some people add to that more V's, but let's not go there. Is it important? You bet. A guy called Seth Steven Davidovich published a book a few months ago called Everybody Lies. Speak for yourself. What the internet can tell us about who we really are. And he says the following: I am now convinced that Google searches that you and I do daily are the most important data set ever collected on the human psyche. He says people tend to habitually lie when they interact with other people, so-called white lies. But people seldom lie when they search online. Why would you deceive yourself when you're trying to find out something about yourself? The Google data set will improve fresh insights on mental illness, sexuality, abortion, advertising, religion, superstitions, health, you name it. Social science will no longer be more than guesswork caused by the imperfection of the underlying data. Social science is now becoming a real science. The person who's going to talk to about this is Mike Ings, University of Cape Town, UCT. He achieved his honours degree in physics and applied maths at Rhodes, PhD DIC from Imperial College in London. He's worked in industry in the UK, in America, South Africa, and he joined UCT in 1988, where he is a professor. He's also a visiting professor at the University of London. He's worked mainly in radar remote sensing, high-performance computing. As you know, there's no area in engineering that is not seriously needed and used by radar. Arguably, it's the ultimate integrative system that we know of. And he's been active there forever. He's authored more than 190 journal and conference papers, 4 patents, supervised more than 90 M's and PhD to completion. He was there when Meerkat was conceptualized. He was there when the South African Centre for High Performance Computing was created. He's played a major role in South Africa's engineering profession. In fact, quite a number of his students are here. Mike, we're looking forward to your keynote. Thank you very much in advance.
So the talk, as Art has given you, is very much trying to define a little bit more closely, but I think, as you can see from my proposed topics here, is to sort of first of all see what is big data and what is hype all about. What caused big data? In fact, I can really only scratch the surface of that particular problem, because I suppose a lot of problems are the ones that lead to solutions, hopefully using concepts of system engineering, and lead to new technologies. So we shouldn't see the creation of huge amounts of data, I think, as a problem so much as an opportunity. And then some ideas of how people are going about handling big data. Some of the things going on in South Africa in particular. This is our own backyard. And then I suppose finally trying to get to the answer, is big data also big hype? And I'll give you what I think, but I think it's really up to you to take away what you've learnt from this. Right, so now the definition of big data. You can go to our friend Google, who is, of course, one of the big players in big data. It's an extremely large data set that may be analyzed computationally to reveal patterns, trends, and associations. Okay? Very much what Art was mentioning, especially relating to human behavior and interactions. We know that much IT investment these days is going towards managing and maintaining big data. Now, next to that, we can place a definition of hype, in other words, as a noun. What is hype? It's extravagant or intense publicity or promotion. For example, his first album hit the stores amidst a storm of hype. Okay. And then there are some synonyms to hype. It's publicity, not a bad thing. We all have to do a bit of publicity. Advertising, promotion, marketing. And then the part that I think some of us don't like so much, which is puffery, propaganda, and then to some extent exposure, although I think it's nice to see in our press when certain people are exposed for doing the things they shouldn't be doing. So it's the thing we've got to be careful of about hype is this puff, meaning to make it bigger and make it look more important than it is. And I think there is a danger in all fields of becoming involved in this so-called puffery. Now, if you look at hype as a verb on the right-hand side there, it means to promote or publicize a product or idea, obviously, intensively, often exaggerating its benefits. And industry quick to hype its products, synonyms for hype are to publicize, advertise, promote, push, boost, merchandise, give publicity, and then, of course, just following on from the noun versions to puff it up, make it look more important, and so on. So we've got to go through what I'm going to talk about now, look at some of the facts, and then decide, is big data really big data? Because big data implies actually a lot of things, as we'll see, or is it just puffery, etc. So what I thought to do was to look through some of the word clouds. Now, I think most of you are familiar with word clouds. What you can do is take a body of documentation, and there are tools around, a lot of them on the web, of course, where you can then ingest those words, and the computer doesn't understand what the words mean. It purely does a bit of a word count and then produces, together with some nice graphics, and this looks very colorful, it tries to demonstrate the words that are occurring most frequently. And as you would imagine, depending on which body of literature or body of documents you look at, you will get a slightly different bias. So I've put together 3 of these word clouds that are centered on the words big data, and to see what comes out. Now, if we look at this particular one here, we get the impression that there's something to do with storing large amounts of data, and the word petabytes creeps in there. Okay, megabytes, gigabytes, petabytes, exabytes, and all these things. It's like that story of the guy who said the temperature of the sun is 6,000 Kelvin, or is it centigrade? He can't remember. In other words, does it really matter for that particular those 2 particular units? The one is just 273 degrees different to the other. But what we've got to realize is that we are dealing with very large volumes of data. And those of you who have even just tried to copy maybe your CD collection across from one server to another new machine that you've got will realize, even with today's technology, it takes quite a while to copy that data over. And this is just dealing with your own personal little pile of stuff. So the other thing that this word cloud asks you to look at is the information in the cloud. And this is a very common thread in big data, is the presence of information. And to find the information, we have to do some analysis. And that is a very clear thing that happens. So big data also implies big analysis. And internet and government are players in generating and disseminating big data. Okay, so that's one set of documents, produced a word cloud, and we see a particular bias to these things. Now, here is a word cloud that must have been derived more from people working in the area of the web, because the view that is coming up here is more the things I think we associate with the web, which is storage, searching, servers, software, and internet. Okay, so it's a fairly simple view of the big data explosion that we're dealing with. Then we come to one that is slightly different bias, and the word that jumps out there, I think, is analytics and server. And then we're starting to see this important word development occurring there. In other words, the handling of big data sets and so on is not a done deal. It's an evolving thing. The data is coming from all these sources. We're going to look at some of the sources during this talk. But the ways to handle the data and then how to get the information out of it is important. Now, information is actually what we need. The data is irrelevant. And an insight I got, in fact, from a friend of mine who's now in the USA, he said, when you look at big data, a lot of people think that it's the extraction of the information that is the important thing. In other words, if you have the ability to extract information from data, you are going to be the wealthy people of the future. This is certainly true, but the follow-on from that is if you don't own the data, you're not going to apply your methods to that particular data. So in fact, there is enormous value in data. The etymology of data, I think, as you all know, is it is the plural that we use as a singular. But the singular is actually datum, but no one talks about a datum. We very loosely just talk about data. And so just be aware of that slight difference. But so big data implies large number of records, and the thing is we have to analyze that set of records, and the important thing is that people who collect data are going to actually be the people who, in a sense, own the mine when we go for data mining. And that's a commonly used term in big data, is to mine it for information. And those of you who've done more theoretical courses will know a little bit about information theory and their ways of defining what information is, but don't worry, we're not going to go into talking about information being 1 over the log of the probability of an event occurring and all that good stuff. So we just have an intuitive feeling that information is valuable stuff, and it leads us to be able to do certain things, come up with new models, and so on. So this is another slant on big data from a particular community, which, as I said, is oriented more to the people who curate large data sets. Right. So what is big data? I've sort of given some thoughts as to that already. So is it the curating of large sets of data? So in other words, does it stop there? Is it the actual collecting of the data? Because we can see to have disks full of data, hard disks full of data, we have to source that from somewhere. And how do we source that? And this is what is leading to the large amounts of data, is that due to our technological leaps, we have electronic digital techniques for creating data that never existed before. And as a consequence, we're now faced with this wall of data. But I think we mustn't, a bit like a surfer when you paddle out to the wave, you don't take every single wave that goes past, and you've got to learn techniques to get through the waves. Otherwise, you are just going to end up back on the beach. I know that from experience. Is big data the extraction of information? Another interesting thing is, do we need to store big data forever? In other words, what is the sell-by date of the data we're collecting? And when we look at some of the sources in my coming slides, maybe we'd look at them and say, well, actually, do you need to store that data? Is there not a process that's generating it forever, and you can go and sample it whenever you want to? And What are the definitions of the total information content of a set of data? So these are all things that we need to think about. Okay, so now we're talking a little bit about the causes of large amounts of data. So I'm not sure if it's clear what that is, but this is back in World War I, and you had all these trenches, and the generals had to tell people to climb out of the tent, rush towards the German or the British lines, get yourself shot, wounded, maimed, blown up. But that message had to get through to say, time to go over the top, as they say. So obviously, this is an innovative way of doing it. And I picked this up from an article about a carrier pigeon that received a medal because it was shot by a German sniper, but still managed to make it back to its hutch with a little message canister around its neck. And it was duly awarded a medal for that. So there is a high-speed communications system from World War I. Otherwise they used telephones, and in fact one of the founder of the CSIR, Sir Basil Shonland, was one of the people who really improved the British communications in the trenches and was promoted up to the rank of major, and they wanted him to stay in the British Army because of the contributions he made to comms. So certainly big data would not exist if we didn't have excellent communications. That has evolved quite rapidly from this kind of technology we're looking at over there. And I still remember when I first joined UCT, a research group in our department was very heavily involved in the X25 data network that Telcom or Post Office in those days had established. And we soon realized, in fact, that this so-called high-speed network, that if we just got one of our Volkswagen combis and filled it up with 8-track tapes, we were orders of magnitude faster in terms of getting data from Cape Town to Johannesburg than the digital network of that time. In fact, many, many orders of magnitude larger. The only problem was that it, especially with the combi I owned, it would have taken 2 days to get to Johannesburg, but once it got there, of course, the content was huge. And by today's standard, all those tapes that we would have packed into the combi, of course, would not amount to very much, probably a gigabyte or something. Now, of course, we have fiber, which connects large parts of our country already and making big difference to our internet browsing and access to so-called big data. And fiber technology is now running in excess of 40 gigabits per second, I should say. And I'm sure the next generation is 3 or 4 times that. And on a more mobile level, we've got LTE now in a surprisingly large number of parts of the country, and this leads to our personal devices having tens of megabits per second of access to the World Wide Web, which again is the potential to absorb or to create large amounts of data, like pictures and movies and so on. So big data has been a while in coming. And on the more analysis side of things, I think probably one of the earlier people, although Art's example trumps mine by quite a few hundred years, is someone who realized that data, when analyzed, could lead to models which could predict things, was Isaac Asimov, who, if I remember correctly, was actually a chemist by training, and I think Russian origin, and settled in the States, and wrote an amazing set of books, including discussions about robotics. And But one of his early books was this Foundation and Empire. And in this book, they talk about this mythical guy, Harry Seldon, I should say, who came up with this theory of psychohistory. And this guy postulated, through models that he developed by observing people, that it is possible to predict, on average, what's going to happen. In other words, history is predictable. We all know that expression, that those who do not learn from history are doomed to repeat it. And we all know that none of our politicians understand that. And we could learn an awful lot from big data, databases, to try and avoid making the same mistakes again. Now, his theory, if you like, the Sheldon's one was based actually on two, and the third one was considered, these are postulates, the third one was considered self-evident. So the first one is that the population whose behavior was modeled should be sufficiently large, so he would say he needs billions and billions of people. The Earth, I think we have about 7 billion, is it now, something like that. But he was talking about orders of magnitude more than that. And he said the population should remain in ignorance. In other words, if you publish the model, then people are going to do the opposite. So you've got to keep it secret, and these are what a lot of the drama in the books is about, keeping this all secret. And then finally, he said that humans are the only sentient intelligence in the universe. These were what his theory was based on. So a very interesting read if you want to. It's a trilogy that made it into 5 books eventually. And the other analogy he draws is that the psychohistory is a little bit like a person looking at a gas. In other words, if you follow the gas at the level of each particle, you're going to have great difficulty seeing what's going on, but you can also develop a macro model, which are our laws of gas, our gas laws, that people observed and wrote down because of empirical information, and it's only in the last 100 years that we've understood the physics behind gases. And so that's the, the kinetic theory. Okay, so now one of the culprits in terms of big data, and certainly subject by the project to enormous publicity. So I'm not saying it's hype, but a lot of publicity is put into this to show that we do have technology in South Africa that is of international standard, and that we're competing and beating, in some cases, international players in the area of radio astronomy. And so this is the square kilometre array, which was an international dream many years ago, to build a telescope which would have a collecting area of a square kilometre. And this was 2 orders of magnitude larger than anything that existed. So maybe 2 orders of magnitude, given tera and peta and exa, all these words that we use in big data, doesn't sound a big deal. But if you think of the physical thing of building enough antennas with collecting area of a square kilometre, you start to understand the difficulties. Now, the organizations come from Australia, Canada, China, India, Italy, New Zealand, South Africa, Sweden, the Netherlands, and the United Kingdom. So these are the original SKA participants. Interesting that the USA is not part of that. They declined to join the SKA. I think they were busy finishing off too many other radio astronomy projects and decided they needed the money to do that properly. system engineers here would be interested to go and read about the EVLA, which I think is the extended something very large array. So it was even bigger. That was actually built using system engineering principles. So that I think was probably the first radio astronomy project to use system engineering in its full sense. And there is some stuff on the web on how that went about, because there was a large commercial involvement in that array in New Mexico. The SKA organization, there was a bid, and the UK won it, and it's now at the Jodrell Bank, where they have that very large radio telescope, which that observatory is now useless because the city of Manchester has grown around Jodrell Bank, and the radio noise is too high to actually do any serious radio astronomy. So the big dish is really just a monument. And there are approximately 100 organizations and companies from 20 countries working on it, with a lot of industrial input to the SKA. So it's heavily supported by the South African government. We can't afford many large science projects, so this is probably the only one that is supported to that extent. The spin-off has been quite large to the country. Tied up with it is the presence of SANREN, which is the South African National Research Network, which those of us associated with science institutions and universities have very good internet and inter-institutional linkages. And we in South Africa are acknowledged as the kind of people who pushed the system engineering process into the SKA. And that is seen, I think, by many as one of our major contributions to the SKA project, was the system engineering that came from South Africa. So let's have a quick look at some of the numbers. I hope those are okay for you to read. So while I'm talking, you can have a look at some of those slides. The figures of what the system generates. Now, there are three projects, if you like, listed at the top. The one is Meerkat, and Meerkat is actually the big brother of the KAT, the KAT, which was the Karoo Array Telescope. So very briefly, an array telescope consists of an antenna aperture, and in the case of KAT was a 15-meter diameter parabolic dish with a feed, front fed, where the signals are received. But what you do is, if you take just one dish and you take the dimensions of that dish, it limits the beam width of that system to, at the frequencies they were working, which is around about a gigahertz or so, limits you to just under a degree or so of beam width. And this is not enough resolution, because when you're a radio astronomer, you're looking at the radiation from celestial objects. And if you want to discriminate two that are close together, if your sensor can only discriminate things that are sort of a degree apart, you end up with a very blurry image of the sky. So what you do is you have a bunch of these dishes that are many, many wavelengths apart. And in the case of the KAT, which was built with 7 dishes, these have got baselines of hundreds of meters, and the wavelength is about 23 centimeters. So you can see, well, if you take the dimension, the maximum dimension, and divide it, so you take the wavelength and divide it by the maximum dimension, you now end up with beams that are really tiny and gives you a high resolution image. The more dishes you have, the more sensitive the system becomes, but it's the lateral dimensions of the array telescope that leads to its resolution. So you've got to combine, and you've got to combine it coherently, as we say. In other words, you have to preserve the amplitude and the signal phase. In other words, the timing of the signals that are coming in. You've got to preserve that very precisely. And this requires high-speed samplers that are running synchronously with one another, spread out over many hundreds of meters in the case of cut. And then those signals are brought back, and now we use digital hardware, namely field programmable gate arrays, to do the multiplications and the Fourier transforms for excising interference, for example, and then combining the signals to form the sky map, if you like. And so the Meerkat was a 7-dish system, and you can see the kinds of data that go into the correlator. So the correlator is this thing that measures the time difference of the signals arriving at the different antennas in the array. And then a lot of that data is contaminated with radio frequency interference, and that gets thrown out. And then the clean data, or the spectral lines for certain kinds of molecules, are then fed back into the science processor, which produces the pretty pictures. And then you want to put the stuff in an archive, where you essentially have a lot of sky pictures, if you want to call it that. And to do all of that, you can see it requires 200 teraflops. The flop is a floating point operation. So quite impressive for its time. So the the cut was some time now back. Now, what's happened is that money is short all over the world. So the SKA grandly in the beginning was going to have 4,000 antennas as part of this square kilometre, but that's rapidly diminished. And in fact, now what they've done is South Africa put forward the money to build a 64-dish, which we called Meerkat, in other words, more cut. And it was slightly smaller dishes, upgraded technology, and it was put together. And the SKA now has seen fit to use quite a lot of that infrastructure into this first thing, which is called the SKA-1 mid. So in other words, it'll have more antennas. I'm not going to go into the exact details of all of that, but you can see there are significant increases in the amount of data and amount of processing required. So we're going from 2 terabits per second to 50. And then SKA2 is going to be an even larger system. And again, it's all going to depend on the money. And you can see that jumps up to 5 petabits per second. Okay. And you can see we're now not in the petaflops, we're going into the exaflop region. And I think at the moment the best supercomputers have barely reached 1 exaflop, or they're heading towards that kind of size. So, huge amount of data, huge amount of processing. So this is a classic big data problem. Good. So we now have the data hierarchy. I'm not going to spend a lot of time on this. This is how they intend to distribute the data. So if you look at that, they're going to be archives where raw data is kept. They're going to be archives where processed data is kept. And then they're going to be disseminations down to sort of researcher level. And that might be something as small as a laptop. And so the tier 3 is where the people who are going to find things with this data are going to operate. So they're a very important part of it. But you must realize, even with today's fast networks, transferring these large amounts of data around is not a trivial task, and it's not instantaneous. You can do the calculations and you'll soon see why. So that's why we do spread the data. Right, so they've created an SKA cloud structure for South Africa. And you can see that there is the research network, so that will be SANREN or SANREN++ for maybe only certain institutions will have enhanced access. And we have connections to the UK, who we work quite closely with, and you can see Netherlands. They're in there as well. And the Centre for High Performance Computing down in Mowbray has a lot of computing power, and they connected into that. And then there is the thing called IDEA. Not so sure I think that was a smart name for organizations. It's too close to another word, but maybe it's supposed to be IDEA, yeah, but we'll see. And you can see IDEA is going to be more about data-intensive astronomy, and it's a sort of Western Cape government-sponsored collection of universities. I think it's Western Cape and UCT are involved in that together with the SKA. And there are also attempts to bring African partners in, and so there will be SKA. And if you remember that picture I had of the map of Africa in the background, there are those white blobs that go out. And right across to Mauritius, Madagascar, up to Uganda, and I think into Ghana, there will be stations. And you can see that gives us baselines of thousands of kilometers to very high resolution. Okay, so that's one very impressive source of data and a need for high performance computing. Here is something that us humans managed to do, and that is just one activity. And there's a very interesting BBC podcast, if you want to look for it. It's about the humble credit card and the influence that's had on financial institutions in the world. Amazing, if you think about it, what you can do with a credit card. Anyway, here's Visa, who I think claim to be the largest retail electronic processing facility. And we see at the bottom there the total number of transactions, although they're worth quite a lot. If you look at the money tied up there and you compare it to our gross national product, it's about 101 billion operations per annum. And even if you ascribe a few kilobytes to that, compared to, say, SKA, etc., it's not really a big deal, is it? So that's just one of the sources of data. But what would be very interesting buried in that data, of course, is what are people buying? Okay. And so the people who own it, which is Visa, have an advantage if they can mechanize that, and I'm pretty sure they are. Yeah, sorry, this is a bit of a crowded slide. The other people who provide an enormous amount of data, and everyone's reading while I'm speaking, so I'll go slowly, is the thing about the social media is here we have another possible tsunami of data, because we all snap off pictures and upload them to social media or to friends, family, etc. And these are sort of a megabyte a shot. So now suddenly there's quite a lot of information. If it gets into Google's hands, of course, they then extract your face. So Google has an idea of every single picture that gets into their storage. They know exactly who is in that picture, as long as you help them out by identifying yourself and your friends. So they ask you to tag them. So you're really helping Mr. Google out quite nicely, as well as other manufacturers, well, other service providers for this information. So you can see the amount of data that's being created by the social media side of things, Google alone was planning to have 10 million servers and an exabyte of information stored on that, and that's purely to handle some of the social side of things. Now, the other thing that is creating enormous amounts of information is this growing thing, and another, shall I say, hype, but probably a worthy hype, is the fact that more and more devices are intelligent in the sense that they can communicate and give you data. I haven't got numbers for what this is generating, but you can see in a house, if you've got a connected home, there's all bunch of games, consoles, so it knows what games you're playing, what you're good at in the game, what you like doing. If you're browsing the internet, if you're watching TV, streaming things, all of that information can be fed back. The weather, sun radiating. The motor car as you drive around can say a lot about where you go. Medical facilities and your mobile device, aircraft flying around, factories, all this stuff is generating data which is ending up somewhere, and there's potentially quite a lot of behavioral information in that data. So the Internet of Things, of course, was helped enormously by the advent of wireless, because that makes it just so much easier to link things together. So what is the cloud? We all refer to the cloud, and it's sort of synonymous with big data, I guess. We get two things really, which is infrastructure as a service and software as a service. And what are the applications, and where did it start and how? Okay, Amazon. They were selling books and stuff and realized they had a lot of computers that weren't being used all the time. And two young South Africans went to work for Jeff Bezos way back. Two guys from UCT, Chris Pinkham and Van Billion, I can't remember his first name. Anyway, they persuaded him that why not use the spare capacity. And they also didn't like the weather in Washington State, and they persuaded him that they should move to Cape Town. So as a consequence, one of the main Amazon research facilities is in Cape Town. It employs probably 150 or more top flight IT people. And they now, and I'm just putting them as an example because there's a strong South African connection to this. These are some of the tools that are now available in there. So a combination of infrastructure and software as a service. In other words, you don't have to buy the stuff yourself. Another South African one at the bottom there is the Lambda service, which I gather was the brainchild of Mark Brooker, who's one of my radar students from some time back. So these services are available, and if you go to Microsoft and Apple, and no, Apple not so much, but Google, you'll find analogous things. So I'm not an Amazon salesman, but just they happen to have a strong presence. So that leads to the question is about build or buy. Because do you really want to have to create something like the CHPC every few years because the technology is out of date? And are you going to use it 100% of the time? And there are a number of web solutions that will help you with that. I mean, I don't vouch for their accuracy. You can do your own bit of system engineering on it. But you can, for example, go to that website there, and you can stipulate what you want to do as terms of processing power, amount of data storage you want, and all that kind of stuff. Move the sliders around, and it'll tell you what that's going to cost you to build. So this particular thing over there It's going to cost me $556,000, okay, to put it together. So if it was my company, I've got to raise the capital. If I go to Amazon or Microsoft, it would cost you $162,000 for a 3-year period. So they amortize it over 3 years, which is probably a good lifetime for a computer these days. So in almost all circumstances, it's not worth doing your own job. And so my thesis, if you like, is that industry is way ahead of us. And is it really worth getting involved in building these complicated web service things when industry is so good at it, and they've done literally the system engineering to pull it together, and they've got instances all over the world. Microsoft already has one in South Africa, and Amazon is talking about next year to create a server in South Africa. The issue, of course, is who owns that data and how secure is it. So there I have to say, yes, there probably is certain data which you don't want to put out there if you don't trust your service provider 100%. But these guys generally are not going to make the data easy. And in fact, they may make it more secure than you could do it yourself, because you're going to have to employ the people to keep the hackers out. The tools to work with big data, there's quite a few around now. So we've got, in terms of technology, multi-core, multi-threading made a huge difference. Caching schemes, depending on your kind of data. General purpose GPUs. Again, for a limited kind of computation, a GPU is not a solution to everything. A lot of people don't forget that. And FPGAs, which are totally reprogrammable, have certain advantages, but very difficult to program. And then, in terms of software at the moment, the king is Hadoop, which is a system. Oops. Oh, sorry. I'm not going to go through this in detail, but Hadoop is a collection of hardware and software. It's based on commodity computing and some open source software. There are a lot of people who understand it, and it allows you to create a high performance computing and high performance data storage system. All the tools are there. So things have come across very nicely. And the people, all the suppliers like Amazon, Microsoft, etc., all support the Hadoop thing. And they're in the wave of research, there are new tools coming out. So these are the Hadoop players in the cloud at the moment. And you can see Amazon plays in both computing and storage facilities. Then in South Africa, what have we got going? Mostly government initiated. There's the CHPC, which is not really a storage place, but more a computational place. SANREN, which is this wonderful network. The Data Intensive Research Initiative for South Africa. The Institute for Data Intensive Astronomy, this IDEA, which is in the Western Cape mostly. The African Research Cloud. The Western Cape Data Center, which is part of the SKA stuff. IBM Research Laboratory, putting money into South Africa. The RSA Data Center from Amazon Web Services coming soon. And Microsoft already have a local center. Now, a very important thing is training, as I say there. That's what we should be spending a lot of time and effort, is postgraduate training in high-performance computing. There is stuff starting to appear. The issue is that this is overarching stuff, and those of you who come from a university realize that many of your colleagues are dinosaurs when it comes to computers. And the other thing is, this is even your technical colleagues, and they're also, deans don't like to lose control of their courses because the courses make money and they don't want to share courses with other faculties. So there's this, they say the fights in universities are so bitter because the stakes are so small. But anyway, there's a lot of opposition to these overarching data courses, but it seems like things are coming right. And so one of the important things people should do is go and do one of these data courses, because you'll learn a lot about how to handle this data tsunami. Okay, so conclusions. There's plenty of big data around with more to come. And as I said, intelligent sensors, the Internet of Things, growing capacity of interconnection, therefore social media, sources of data. Then there's the growing power of analytics and, of course, artificial intelligence, or AI. A friend of mine talks about the artificial intelligentsia, but anyway, let's assume that they are actually producing good stuff. Deep learning is another hype word that's out there. So a great deal of it is hype, but the field, I think, is well-founded. In other words, it's a real thing. There is big data and the need for big processing, and but it's not the answer to everything. Some intelligent use of this proper design, i.e. system engineering, is going to help you. I think industry is way ahead of governments, and I really think governments shouldn't bother with trying to create these facilities. They should rather pay companies to do it. It's an ideal private, what they call it, public-private partnership, as long as a certain nefarious accounting firm doesn't get in the way. Security, big issue. So maybe there is stuff that's burned before read, and you don't want to do it. Don't store everything. I mean, I would argue, why does the SKA store all this raw data? I don't think the universe is going to change very much in our time. And so I think you can always go and look in a particular area whenever you want to. Okay, there's a sequencing problem of sharing the instrument, but I don't see that all of that data is necessary to store. And tied up, with that security thing, is how independent is the industry that's providing your service of its home country? In other words, mostly the USA. In other words, can you trust Amazon not to be feeding your information directly into the CIA or one of those agencies? That's not my field. So I've overrun slightly, but I might have caught back a few minutes. And if there are one or two questions, maybe.
I have a question around data communication. So the challenges that have been addressed, be it security, cost of storage and computing power being in the cloud and so forth, but there's still the issue of data communication, be it cost, infrastructure, and so forth. How is that challenge going to be addressed in the future to enable that this big data, there's access to big data analytics and cloud computing?
Yeah, there's a lot of work obviously needed for that, and what's quite interesting, because I happen to be doing quite a lot of work with Amazon on some radar processing, is they have very sophisticated models for the computing. In other words, if you have a job that needs, say, 1,000 processors, I can't with ease get that done in South Africa, so for a few cents, literally, I can instantiate 1,000 processors. And I pay so many cents for that, US cents. If, for example, I'm prepared to wait a while, I put a bid in, and they look at their load, and when they've got a spare gap, they'll run it at the price I said I wanted it to be run at. So I might have to wait minutes, hours, days, but it'll run. Same thing, if I have a data set, for me to have my data coupled directly on a high-speed network to the processors, it costs me a lot more to store the data there, and they charge me for every access. But I can go into what they call their glacial storage. So I can put some of the older data into a store that is about 1/10 of the cost per month to store it. But we're still talking of a few dollars a month to store terabytes of data. So the high-performance computing people understand that what I call adjacency of data and processor very well, and their techniques for handling it.
Duarte's got a question.
Okay.
Sorry, Ed wants me to ask a question, so I've made one up now. No, this is a real question. Thanks for the presentation, Mike. Nice to see you again. The one question that perhaps you didn't touch on was the issue of purpose. So there seems to be what I've perceived, and perhaps this is just my imagination, but there are people who imagine that if we just put together all of this data, we can suddenly discover new things. So the issue of reasoning and finding relationships is really an important one, which is a human reasoning thing. So why do we have this data? How is it? So we have more data but less knowledge and wisdom, this problem. How do we get to the issue of purpose and why we're doing this and the reasoning behind that?
No, that's exactly right, and that the people who are going to make money out of it are the ones who have the purpose. In other words, they're going to go to Visa and say, look, for $100 million, I'll buy your transaction database for a year. Then they're going to run some deep learning on it, and they'll be able to tell certain suppliers what people like, what they didn't like, and provide marketing information, for example. So, as they say, the people who understand data science and with a bit of reasoning will be able to make a lot of money. Very much like we dug gold out of the ground in the past, we're going to mine information out of data sets. So to blindly put a data set together is silly. As I say, I think you must think hard, why am I doing this? And obviously in the case of Visa, they do that for compliance reasons. The governments want to know about transactions and money laundering and all that sort of thing. So there are reasons they put it there, but there is data to be mined out of these things. So it's a mixture of these kinds of, this kind of thinking I think we have to apply. But certainly never just dump data there in the hope that in the future something will come out. But on the other hand, we wrote things like the Doomsday Book, which was a record of every person and how many cows he had in the UK. And that's invaluable now for getting an idea of how things have changed. So, sometimes maybe you just store the stuff and something will come out of it. Okay.
Mike, on behalf of all of us, I'd like to thank you very much indeed for a very insightful keynote. You have described the problem, you've structured it so that we can better talk about it. You've spoken about the build or buy issue, you've spoken about the security, what industry is doing, and of course the state of the art. Thank you very much indeed. It is customary, Mike, to give you a very small token of our appreciation. Thank you very much. It's not the real present, but I'll talk about that in a minute. But thank you very much for your time.